Hey there.
Nice.
Oh, you're muted?
Sorry.
Yep. How's it going?
I'm good. I like completely missed your text.
It's okay. So, yeah, what's new?
As far as studying go, I was only able to do Anki and just reviewing stuff in the end. Um, so what should we do for today?
So yeah, what do you think? Um, because yesterday you said that you didn't feel comfortable or confident in some of that physics material. Um,
I feel like that's probably the case, but I don't know. I feel like revisiting the Jack Weston isn't like as productive as I assumed it would be because I remember like the explanations and how we went over it the first time. So it's like not, it's the same thing that you were saying with like redoing an MCAT.
uh, well, I mean, it's a little different because you mentioned that there were areas in physics that you didn't understand, so that's where you can get questions for that material. But um so okay. um so are you saying that you like understand that material now, or
Well, I understand the questions that I did, but like when I'm shown new ones, I don't know that it's gonna carry over.
uh well, okay, yeah, like so let's see, I mean, like, maybe you can kind of like explain to me like why the answers are the answers, or I mean, we can also do like maybe like section bank stuff. But
Yeah, I think let's do that.
yeah, the only reason that I suggested that we look at that content diagnostic is because you specifically said that you were, you know, you weren't where you wanted to be in terms of understanding the physics of it. So that would be like the way to address that directly.
Yeah.
Whereas, in a section bank, it's not going to directly really ask you stuff like that.
Sure.
So, um, but you're saying that,
Well, what do you mean that the section bank won't ask me physics questions?
I mean, so like if you're having trouble understanding physics concepts, the section bank isn't going to directly test you on those concepts. So, but you need to have the concepts down to be able to apply it to the passages.
I understand.
So,
Section
and
bank is passage based, not just.
it's also mostly because you said that you didn't do the test on over the weekend because you didn't feel that you understood the physics stuff. So that's why we did that. Um,
No, I completely understand. I just, yeah, okay, so let's just go over more Jack Weston.
I mean, we could do the section bank, um, but
I just forgot that, hold on, I'm confused. Oh, yeah. I just forgot when I was looking at it that, sorry. I forgot that the, section bank has like passage based stuff and that it wouldn't be showing like specifically what I wanted to review. So that makes sense.
yeah, yeah. So yeah, since you mentioned like the physics stuff, that's why we did
Yeah.
yesterday. Um, but yeah, it's up to you what you want to do.
Let's just do these.
Okay.
Um, oh, save the math.
Hmm. Yeah. So how do you do?
So grams to kilograms probably would be my first step.
Okay.
That would be 0.2
All right.
kilos.
Okay. So then what?
So isn't it that since the object isn't moving, that these two are equal, the F net is zero, so if the um gravitational force is 10, then the force that goes in the opposite direction is also 10.
Where are you getting 10 from?
10 newtons per kilograms is the acceleration due to gravity.
All right. But how would that
Acceleration, but I'm thinking like if we yesterday we were talking about F net and how since normal force and gravitational force are opposite from each other, then those like because the object is stationary, then they cancel each other out, so F net ends up being zero,
sure.
right?
But
So
what is it asking for?
it's asking for magnitude of normal reaction force and from the table on the book.
Yeah.
Right. So
How would you solve for that?
it's 10 over 2 kilograms, right? 10 newtons over 2 kilograms. No.
What do you mean?
No, I'm trying to like use the so the mass of the book is 200 grams and the weight of the book, but I'm not sure how to do that.
So what's force?
Work over distance.
Okay, but another way of expressing that, like the most simplest way.
Newtons per kilogram.
Well, what do they say that?
F equals ma
Okay.
times acceleration.
All right. So
So the math is 200 grams, which is 0.2 kilos
okay.
times 10 newtons per kilograms.
Mhm.
Kilos cancel out and you have 10 newtons times 0.2 and you get 2.
Yeah. So yeah, so you definitely need to know about force. That's very important, of course.
So
And
why do they have the weight? Is that just to throw you off?
wait, what?
Why do they have the weight there? Is it just to throw you off?
No, because there's a weight there. Like there must be a weight, right?
Right. But why is it included in the question stem?
Well, if it didn't have a weight, like you can't not have weight, you know? If something has a mass, it must have a weight.
Uh-huh.
And the normal force is going to be basically like the table in this example, like going in the opposite direction from the weight. So when you have a free body diagram, you need to, draw all the forces that are being that are there.
Acting on the okay. All right. What did they say?
Basically what you said, but just remember that force is a mass times, and also the units here can help you out. If you know that force is in newtons and you are given kilograms, then you can just multiply it by this to get.
That's what I was trying to do. And then I got confused. I feel like I get in my I'm so sorry. I get in my own way a lot of the time where it's like I start to think about it correctly and then I like assume that I'm doing it wrong and then I give up.
Yeah. You wanna, I guess, have a structure to how you approach the questions. Because I think the way that you initially approached it was by saying F net is 0, which is true, F net 0. And then when we talked about force, you went at it using work, but we don't have any information about work here. So, or distance, right? It's not really moving. So what we have is mass, and you need to know how to take mass and turn it into a force.
Mm-hmm.
Yeah.
Okay. Air has a density of about 1 kilogram per meter cubed. So we talked about this. Is the equivalent, like centimeter cubed is equivalent to e to the 6th, was it?
Of what?
Centimeters.
Wait.
Do you remember there was like a conversion that we did that you told me to memorize? Like it was whatever the centimeter cubed was, it's centimeter e to the 6th,
Okay. Well,
right?
I mean, yeah, we did something like that. But what would it be though? Like, because this is in 3 dimensions, so that's a volume.
Right. So you would have to cube root that number.
Well, we could uh convert it into like cubic meter.
Yeah.
So, so for instance, if we had one, so if I were to convert regular centimeter into meter, it would be 1e negative 2 meters is equal to 1 centimeter, right?
Yeah.
And then from there, you can do, okay, what if we want a square centimeter?
1 e to the negative 4th.
Yep. Square meters.
And then 1 e 12
Um, so
or 16. No. Hold on. Do you add to the negative 4? Is it negative 7?
it'll be negative 6 because,
I did remember it correctly. You just made a face when I said 6. I thought I was doing it wrong.
well, that because you're just telling me 6, but you're not telling me like
Yeah,
you're
I know.
saying that as a number. Um, but but this is showing you that for a, because the thing is, if you take this and you cube it, cube both sides, right? This turns into 1e. You multiply the exponents if you're cubing it, or taking an exponent to the power of another exponent. So that's what'll give you the negative 6 cubic meters for 1 cubic centimeter.
Mm-hmm.
So, so basically, a cubic centimeter is 1 millionth of a cubic meter, or a cubic meter is 1 million cubic centimeters.
Yeah, that makes sense.
Hmm?
So 6,000
Mhm.
e to the negative 6th m cubed
Mhm.
times
Mhm.
1 kilogram per meter cubed. Meter cubes cancel out, and so you're left with 6,000 e to the negative 6 kilograms. And then a kilogram is the same as 100 grams or 1,000 grams.
Which one?
1,000. 1 e⁻³ So then you're left with e⁻³ And that's the same as 6
Mhm.
kilograms.
So we got rid of the kilograms, right?
Yeah.
So,
So you just have grams left. So 6 grams. Yeah.
yep.
Cool. So once you have this figured out and apply this, it's an easy enough question. I remember we spoke about this and we solved out the ratio and how there was something specific like about like the scenario because it's a sphere and that like the density to volume ratio was 1/2 in this circumstance, or it was 1/4, and then because it's half of it, it's 1/2. Or
Uh, I
something.
mean, just solve it like how you would normally. Um, so how can we like approach this?
Okay, so well, they're telling us what it's to solve for PS over PW.
Okay.
So how does that equate to volume though?
So, uh, this is a buoyant force problem.
Mm-hmm.
So, um, what can you tell me about buoyant force?
I don't know.
Okay. So,
So forms or something I need to go over.
yeah. So let's say that we have some vessel of water or something. Yeah, water, I guess, in this case. And we have this sphere that's halfway submerged. Now, buoyant force or Archimedes law or principle or whatever states that a submerged object will displace its own weight in whatever fluid it's submerged in. So, so you want to start off like most of these physics problems with like a free body diagram.
Mm-hmm.
So I started it off over here. So what forces can we draw on this?
I'm gonna say that you have the force that the object is exerting on the water, and then the force that the water is exerting on the object.
Well,
Right? Because it's not like a wave situation where we have to take into consideration
so what kind of force would act on this?
the buoyant force, and then I think there's still the force of gravity,
Yeah.
right?
Yeah. So start off with that, like foundationally speaking, whenever you draw a free body diagram, remember gravity is going to be present, right?
Right.
And that goes for yesterday we talked a lot about like just doing something as simple as changing the height of an object changes its what?
Changing the height of its object changes like the work that needs to be done to lift it.
So, but tell me more so in terms of, what type of
Well, we were talking about like the greater the length of like a lever.
no, just think of a regular object.
Yeah.
You lift it up to a higher height. What changes? The type of energy.
Oh, the gravitational potential energy increases. The higher the object is off of the floor. I guess I'm confused with like water because like you assume like water level
So
is
just start with the foundational stuff, right?
right.
So foundational, right? Gravity, it's always present. I mean, they're not going to give you like a question about in space or whatever, likely not. But you always want to remember gravity. So if something's height moves, before you think of friction or anything like that, or work even, uh, understand it in the context of energy. If you lift something from one height to another to a higher height, um, you're increasing the gravitational potential energy of that object,
Mm-hmm.
right?
Yeah.
So now for this, before we think of anything about water, we start with what we know to be true in all cases, which is that it's going to be experiencing a force of gravity, right?
Mm-hmm.
So we're going to start with drawing a vector going down for gravity.
And so that's 10, which is the one that we should think of it. Or this isn't important right now.
What are you saying about 10?
Like I'm saying 10 newtons per kilogram or 10 meters per second squared. Like why are there so many different ways to write the gravitational
Well, they're
stuff?
essentially the same thing, but so I mean 10 meters per second squared is in units that are more useful if we're using it as an acceleration,
Mm-hmm.
right? And F equals ma.
Yeah.
Well, this is g, right? So F equals mg. Now, if we solve for g, we can divide mass on both sides to get force over mass is equal to g.
Others.
Now, that means force of 10 newtons over 1 kilogram. Now, they're both the same, except this is good for acceleration purposes, but this is the gravitational field strength, meaning in Earth's uniform gravitational field, um, a 1 kilogram object would experience 10 newtons of force.
Mm-hmm.
So you want to be able to be flexible with the type of unit conversions here, uh, to see that it's ultimately the same thing, but it could be expressed in different ways, right?
Yeah.
So, okay, so now gravitational force that this experiences would be, how can we express that?
Well, haven't we expressed the gravitational force as the FG?
Well, yeah, but that doesn't say anything. Like, what is it equal to?
10 newtons per kilogram.
So,
Meters per
so
yeah.
if this was like, let's say it's a planet. Well, that's a bad example, but let's say it's like a building. Let's say it's like the Empire State Building. You're saying the force of gravity that it experiences is just 10. It weighs 10.
It's a ratio of like the
So
mass,
think back to what force is. So what's force?
the work over distance.
So so just think of it. So like just
Mass times acceleration.
yeah, right?
Right. So greater the mass of the object, the
So
greater the acceleration.
what do we set equal to here? What do we set this equal to?
Meters per second equals mass
So
times.
this will be the force of gravity, aka the weight,
Mhm.
which would be equal to what?
Mass times acceleration.
Okay. And the acceleration value that we use, what would that be?
10
Huh?
meters per second
So
squared.
mg, right?
Yeah.
So remember that.
So
Remember that
MGH. Yeah, this is that. But
what?
we don't have the height. It's MGH, like that component of gravitational potential energy. But we don't have a height, so no, it's just MG.
So yeah, remember that because this is important. Like when you like so like in physics, like forces are like the first thing that they teach you.
Mhm.
So you want to know, like they teach you force before they teach you work and energy. So when you think of force, like sure, we can say that it's work divided by distance, but a more like elementary uh definition would be mass times the acceleration, or in this case for weight, mg, right?
Mhm.
So you want to be able to do that. You want to be able to see, okay, this thing in the free body diagram experiences a force of gravity, and the force of gravity is mg, the mass times the, in this case, this gravitational acceleration, right? So, because what you were saying were like, you were saying like a unit, like, and then you're saying like 10, and you're just kind of saying a lot of things, but remember, a force, if you think of Newton's second law, like the sum of the forces equals mass times acceleration, right?
Mhm.
So gravity is a type of force, gravitational force. And so it's, and it determines the weight. And so that's going to be the mg here, right?
But yeah, okay, so that's this force.
What are you saying? The one that, the arrow here? Yeah.
No, I'm saying like we have this one figured out and then never mind. Sorry.
Mhm. So, okay. So this is the force of gravity, aka its
All
weight.
right. Yes.
Now, since the force of gravity is what's pulling it down, right?
Mm-hmm.
Force is just like friction or air resistance. Like if there wasn't the force of gravity, you're not going to have a buoyant force. It's a consequence of that force of gravity. Same thing with friction and air resistance. Like that doesn't exist on its own. Like, you know, but if there's like a force on it and, you know, it causes it to move, then yeah, you're going to have that friction and air resistance. Now, the buoyant force will be in that opposite direction, going up like this.
Mm-hmm.
And now the formula for buoyant force, which is important, is going to be rho, which is the density of the fluid, or in this case, the water. So I'll write rho H2O, volume of the fluid that is displaced
Oh.
times G. Okay.
Mm-hmm.
Now, rho, which is density, would be mass times volume, right?
Yes.
So if we do rho times V, it would be mass over, did I say times volume? I meant over volume. So mass over volume for the rho times volume gives us what?
Mass.
Yep. And so rho VG would give us mg, right? It would give us like an equivalent of that, right?
Yeah.
Okay. So the buoyant force will be written like this, and the weight typically will be written like this, right?
Yes.
mg. But
Mhm.
one of the key things to do for buoyant force problems is to be able, I use green, to be able to express this in these terms, meaning rho of the object, volume of the object that's submerged, times g, right?
Yeah.
So now we have, because if they're asking, the density, like to find the ratio of the density of the sphere compared to the density of the water, how can we like even get an
Well, okay, so we were talking about the velocity of the displaced object. Isn't the water what's getting displaced? And then the row would be the row of the sphere.
so okay. So first of all, so this mg force of gravity, right?
Yes.
Now, from that, we can't figure out anything about density of the object. So the first thing that you want to be able to see here is that we can put it in terms of rho times volume times g. That's how we introduce rho of the object into this like free body diagram that we're making.
Yes.
So that step is crucial. I want you to make sure that you see that step. Okay. Now we can actually do stuff here. Because if this is just floating like this, it's not moving, right? It's not going down or up.
Mm-hmm.
And if it's not going down or up, what would the net force be?
0.
Good. So now let's write that out, right? So we can have buoyant force minus force of gravity. You could have it the other way around too, but since they're in opposite directions, one is going to have to, like, one of the vectors will be positive, one will be negative, right? And so this is the sum of the forces, which is F net. Whoops. And this will equal, what's the acceleration?
0. There's no movement.
Good. So that's 0. So now we can just rearrange this, right? We can add force of gravity on both sides and get buoyant force is equal to force of gravity, right?
Yeah.
And then buoyant force is this. So it's rho H2O times volume of that fluid displaced times G is equal to rho of the object. Oh, I guess they say that they use S, so I'll use S, rho of the sphere. And then volume of the sphere that is submerged times G, right?
Yeah.
Okay. Now, since this is halfway submerged, right?
Mm-hmm.
That would mean that these red, that the volume of the fluid displaced, or the water displaced, is equal to 1/2 of the volume of that sphere.
Mm-hmm.
Okay. So now for volume of the fluid displaced over here on the left, we can just plug in 1/2 volume of the sphere, right? That way we get a common volume of sphere term.
Wait, I feel like I don't understand this part. Like the red. I'm sorry. Can you?
Yeah. So let's see. So does this part make sense?
This, yes.
Okay. Now, since they're saying that half of the sphere's volume is submerged in water, right?
So it's 1/2 of the solid, right? Of
So,
sphere.
so the volume of the fluid displaced is going to be equal to 1/2 of the volume of the sphere.
That makes sense.
And so now we can plug in. So like here is the volume of the fluid displaced. We can plug in 1/2 volume of the sphere, and then you would get like term. You would get the volume of sphere on both sides, right? So rho water, and then I'll put 1/2 volume of the sphere times G is equal to rho of the sphere, volume of the sphere, right? G, right?
Right. And then row of S and row of H2O, we said were equal to each other. So do you cancel all the values except for 1/2?
Wait, those won't be equal. If they were equal, the answer would be 1, right?
Right. Okay. No, you're right.
So, but yeah, we want to figure out the ratio of density of the sphere to density, like over density of the water, right?
Mhm.
So we want to divide both sides by density of the water, and divide both sides by volume of the sphere and g, right? So I guess I'll do it in like 2 steps. So first, let's divide both sides by rho of the water. That means on the left side, you'll have 1/2 volume of the sphere times g is equal to rho sphere over rho water times volume of the sphere times g, right?
Right, but can we not cancel out volume of sphere and G?
Yeah, yeah. So yeah, I was doing
Factor them out at least because they're like present on both sides.
yep,
And
yep.
then
So
one
I was
is
just doing it in 2 steps, but yeah, now we can just divide both of these on both sides.
mhm.
And there we
Yeah.
go. We get 1/2 is equal to the rho of the sphere over the rho of the water.
Okay, let me explain this back to you.
Yeah.
So first we thought about like density of like water, how an object in water would act. So we realized that the bottom factor would be the force of gravity, and we wrote that as mg because mass times acceleration, acceleration is due to gravity. And then on top we did the buoyant force, which is rho of the object times velocity times gravity.
Try again.
Try again.
Yeah.
Rho of the water.
Yep.
Okay.
And then
Um,
the volume is going to be the volume of the fluid displaced.
Displaced, yes. Then we went over here. Or no, what was the
Then
next?
it would be this step here in green.
Okay.
So that's a critical
Then
step.
we rewrote gravity as rho of the object, velocity of the object
Volume.
times gravity.
Mhm.
And then we set those two equal to each other to create a ratio. And then we substituted the volume of the fluid displaced for 1/2 of the like velocity of the object because of half of the sphere's volume was submerged in water. So we created like values on both sides so we could put set this equal to each other, like instead of this like a velocity of the sorry, volume of the object, we have 1/2 volume of volume of displaced water, we have 1/2 volume of object.
Mhm.
And then we divided out rho of H2O so that then we were left with so that we could create our ratio. So we were left with 1/2 um volume of the object times gravity is equal to rho of the object over rho of water. And then we got rid of Vs and G and we were left with 1/2, which is our ratio.
Very good. So
I need
now
to like over so that I can.
what's up?
I feel like that helps me like to talk it over and so that
Yeah, yeah, yeah. So great job. And now something that can help for the future is knowing,
the buoyant force equation.
well, yeah, of course, but rho of whatever object over rho of water is going to be something called specific gravity. This thing.
Okay.
So, like, what helps me remember is like, because when I first learned about specific gravity, I think it was like in Gen Chem, and the specific gravity of Mercury is 13, which means Mercury is 13 times more dense than water. So rho of something over rho of water is going to give you something called specific gravity.
Okay.
So
Cool.
like if we know that if we know that half of the sphere is submerged in water and it's floating, right? We know that its specific gravity, if it had the same density as water, specific gravity would be equal to 1, right?
Yes.
Right? And if if the density of the object was more dense than water, you would get a value larger than 1, right?
But I thought we set it up in a fraction where it's like object is, oh yeah, yeah, it is. It's the numerator. So yeah, it would be greater than
Yep.
water.
And then if something is floating, it must have a smaller density than water. So the specific gravity would be less than
Less
water.
than, yes. That
So
makes,
now we know for the future, if they ask us something like that, we can eliminate C and D right away.
oh,
Mhm.
that's cool.
Yep.
All right. Wait, hold on.
Oh, did you want to screenshot?
Let me go back to that question so that it's all together.
Mhm.
Perfect.
You got it? Mm-hmm.
I'm waiting for, oh, it did not go away. All right.
You got your screenshot?
Yeah, I did. I got it.
What's up?
Sorry, yeah, I got it. Sorry, I'm only sharing the Google Chrome, so it's I
Mm-hmm.
don't know if it's showing you when I take a screenshot.
Yep.
Um, nanometer, manometer, not nanometer, is filled with liquid mercury and used to measure the air pressure inside the balloon. I remember this problem.
Mm-hmm.
Which height is 50 centimeters? For pressure of the balloon, air inside the balloon. Okay. Um, so we're using liquid mercury, and I remember you were saying that like because of where it is, the pressure is like if it was here, it would be a different answer. Like I remember us speaking about this problem, but oh, because gravitational something, right? It's acting on. Hold on.
Mm-hmm.
If our height of 50, we start with this value, the 14,000 kilograms per meter cubed. Well, because we're looking for the pressure of the air inside the balloon. But this is, okay, the density equation, right? Which is, wait, shoot, I forgot.
So let's think about it conceptually, right? So this part over here, what is it exposed to?
Air and mercury.
Well, I mean, it is the mercury, but what is it exposed to?
Air pressure.
Yep.
Ocean
So,
air.
atmospheric pressure, right? So PATM. And then this would be the pressure from the manometer balloon, right?
Mm-hmm.
Right. Now,
ATM was 700 kPa.
well, let's just do this conceptually first. So this part is exposed to the atmosphere, so it's going to be experiencing an atmospheric pressure, right?
Mm-hmm.
And then this part is exposed to the balloon, so it's going to be experiencing a pressure caused by that balloon, right? Now, is one greater than the other, or
Yes, obviously, because it's able to push the mercury down here.
all right?
So this great of a displacement of 50 centimeters.
Okay, so uh, so that means what?
That means that the pressure of the atmosphere is greater than the pressure of the balloon.
Excellent. All right, and then what do they say the atmospheric pressure is?
1 times 10 to the fifth PA.
All right, Now,
What's in kilopascals. So we can convert this to kPa right away, right?
okay.
Is that necessary?
Uh-huh. So
So
yeah.
it'd be 1 times 10 to the third.
Um,
No, 1 times 10 to the second.
good. Which is 100 kPa, right?
Yes.
Now we know that it's going to be the atmospheric pressure is going to be
Has to be less than 100. So it's either C or D right away.
uh,
But because it's so much lower, we know that it's D because then the height wouldn't be such a great
well. So okay. So the first thing that you said was right.
direction.
That P pressure of the balloon will be smaller, right? Smaller than atmospheric pressure, which is 100 kilopascals, right? So we can get rid of A and B, right?
But then I was saying that 93 is so close to 100 that but I guess it just depends on like the scale of the object. Like if they drew it like and it was significantly smaller, I wouldn't come to that conclusion right away.
Well, no, now like the way that they're drawing it is not going to be helping us here. So now we have to do the math to figure out if it's 93 or 30.
Okay.
Like there's no way for us to say like, all right, this isn't this is pushing it down a larger amount, like compared to what, right? So, but yeah, you can definitely just from looking at it conceptually, eliminate A and B at least. So now,
Now,
yeah.
I really feel like it's something with the 50 and the 1400 kilograms per meter cubed, and that we have to convert centimeters to meters cubed.
So let's like actually try to like
Think about.
yeah. So yeah. So the pressure of something like this is going to be like the pressure plus the pressure of the atmosphere plus the pressure of like this column of mercury here, which would be rho gh.
Mhm.
And so um and so for like this side on the left, we can say that, let's say like left, right? That the pressure is PATM plus this column of water of mercury, like this thing over here is the rho GH part. So that's the pressure from the on the left side. Pressure on the right side is going to
The
be
balloon plus rho GH.
what's up?
Would it still be pressure of atmospheric? Wouldn't it be pressure of the balloon on the right?
Uh-huh. Yeah, so that'll be what this is over here. And since it's uh you know, the water column or the mercury column is larger in this direction, that means that this pressure of the balloon is going to be decreased by that rho GH amount.
But it's still pressure of atmosphere, or we're just doing that on purpose, so we're not adding in additional values.
Um, so yeah, we know that like
There's always the atmosphere acting.
yeah. So like when I said that yes, the atmospheric pressure must be larger than the pressure of the balloon. Um, what that really means is, or it's larger by how much, right? Or the balloon's pressure is smaller by how much, and that's where this rho GH term comes in. That is by how much, the
Right. But then isn't it negligible if it's like one is adding it, one is subtracting it?
I mean
If it's picking
overall,
up a ratio between them, right?
well, overall they're gonna be like in terms of like this, like they're gonna be like equal because otherwise this is gonna be moving around, right? But this lets us figure out, uh, for instance, pressure on the right side, aka the pressure of the balloon. So P balloon is this.
Mm-hmm.
So
All right. Um,
Mhm.
So 100. Hold on, I'm missing my annotate. Let's just say 100. Yes. Oh, thank you so much. And then rho gravity
Mhm.
10 times 50 centimeters. Wait, it's in meters, so I might as well make it 50 centimeters into 0.05 meters.
So let's start with the row. What's the row here?
104, sorry, 14,000 kilograms per meter cubed.
Okay. And then,
We have our thing to convert centimeters to meters cubed, and that was e to the negative sixth.
so we're plugging in these values. So row is this one, and then
Gravity is um
Mhm.
mass times acceleration, so 10 uh meters per no, I don't want seconds. Kilograms per newtons.
I mean they're giving us that.
It's per kilograms.
Yeah. So 10 Newton.
I was just trying to think of like anyone that would give me a value that like because newtons, how are they going to cancel out?
Um,
So
well,
now we have like kilograms and kilograms that are canceling out, and now okay, I understand. Never mind. And then the third thing is height, which is 50 centimeters.
okay. Now how
50 e to the negative sixth meters cubed.
uh so we're plugging in this, right?
Right, but the height is 50 centimeters.
Yeah.
And I'm trying to convert it from centimeters to meters cubed.
Well, why would you do this? So height is in one dimension,
Okay.
right?
Right, but I'm okay, never mind.
Mhm.
So now my kilograms are gonna cancel out and I'm gonna
What are we putting for the for H?
centimeters. Or can I have meters?
Okay. So
So it's 0.05 meters,
um
isn't it? 5, 50, 1, 2, 3. Oh no, it's just 0.5.
0.5, right? Okay.
All right.
So yeah,
140,000 newtons per meters cubed times 0.5 meters,
uh-huh. We could
right?
we could treat this as 1/2, and then that times 14,000 is 7,000,
Mm-hmm.
and then 7,000 times the 10 would be
70.
70,000, right? And we get rid of the kilograms here, and then this meter, and then
And this, so
turn.
it's meters squared?
Yep.
Yes.
Because if you remember,
Right.
force over area is pressure, right?
Right.
Which
So
means newtons over square meters, right? Right.
so that means the newtons over meter squared is the same as PA.
So yeah, it happens to be equal to a Pascal, but the more important thing is seeing that pressure is force over area.
Okay.
And you see how we end up with newtons over meters squared, which is the area part.
Right.
So, because you wanted to change this into cubic centimeters, but
I understand.
we're
That's not
not like that.
necessary.
So, okay, so we have 70,000 pascals, which is how many kilopascals?
70
So now we have 100 kilopascals minus 70.
minus 700 because we solved for the mercury. And we're left with 30.
Yep.
Cool.
So now, yeah, explain it. Mhm.
Okay, so all right, here's how we started this out. First of all, we crossed out the first two because I realized that PA could be converted, sorry, the pressure, atmospheric pressure could be converted to kilopascals, and then 1 times 10 to the fifth would be the same, and pascals would be the same as 1 times 10 to the second kilopascals, which is 100 kilopascals. And obviously these two are greater. And the reason why we know that these two cannot be greater is because looking here, we obviously see that like you're pretty much looking like if the pressure of the balloon and the atmospheric pressure were equal, then the two like heights would be the same. And since the one that's where the atmospheric pressure is acting on it, that it's lower, then that means that that has a stronger pressure.
Mhm.
So yes, that's how we crossed out these two. And then for the second two, we obviously had to do the math because we couldn't just say that 30 is smaller. So what we did is we set up a proportion. And so for we had PATM, which is like atmospheric pressure, and then we created the rho GH, which I can't remember where that came from, the rho GH.
Yo, yeah, yeah. So I guess typically you'll see it in questions about like, let's say something is at this depth, right?
Uh-huh.
What pressure it experiences. Because if something's just floating up on the surface, it's only going to be experiencing the atmospheric pressure. But if
Right.
something is submerged, it'll experience both the atmospheric pressure plus the pressure of the water, or like how deep it is underwater, right? So that's where
Mhm.
the rho GH term comes in.
Right, because it's
Hmm.
still the same gravity thing like we did in the sphere, right? Essentially. Okay.
Yeah. So like,
So, but because on the left side, wait, but now I don't understand why the right one it's negative and
oh yeah, just
it's up
just as uh I
because
guess
it's greater on the left, like it's lower.
yeah, yeah. So so if we want, so we know that the left side has the reason I made it left and right is just because both terms will still have PATM. So
Right.
I wanted to differentiate like PATM from just the pressure on this left side over here. Um, but we know that the pressure on the left side is going to be larger, so we can treat this column of mercury as rho GH. And so
And
that's the
right,
that the left side uh has that is more than what the right side has.
understood.
Now, yeah, John. Mhm.
Would it be like completely wrong to think about like gravitational potential energy and how when you were saying that the higher you raise an object, the
Mhm.
more the pressure acts on, or the more gravitational potential energy. So this is kind of like the inverse of that. So because it's lower, there's more pressure. So that means the rho GH has to be positive and here it's negative.
Uh-huh. Yeah,
Okay.
yep. Now let's say though that, because remember when you said that this was 0.05,
That I calculated it wrong?
like let's say that, because we talked about it and then you realized it was just 0.5, but let's say you did the 0.05, right? This would
Right.
end up
But I would have solved it out and gotten a similar value. But the thing is that I'm worried that I would have solved this and not realized that we solved for mercury and that I need to subtract it from the 100 atmospheric pressure.
so if you used this value, right,
Right.
you would have ended up instead of with 70s,
Got it.
right?
Right.
Which would lead you to the 93,
Uh-huh.
right? So you see uh how like a simple mistake like that can lead you to like a wrong answer choice.
Hmm.
So
Yeah, I understand.
and like a larger, more than a fifth of the people who took this, and you can kind of see like, okay, this is where what most people chose, and that's if they did this, if they took the PATM of 100 and added the 70 to it, right?
Yeah.
And then C would be where 21% chose it, and that's if they mess this calculation up to get 70. I mean, sorry, to get 7, because then 100 minus 7 would be the 93. So you're yeah, so like sometimes you can get lucky, and if the answers are totally nonsense, then yeah, it can help to like figure it out that it's the 30. But a lot of other times the answer choices will be like valid, uh, answers, like somewhat valid answers, like but with like some type of little mistake. So, but yeah, so here I guess the best way, yeah, the way that you described it, pretty much perfect.
So,
Here's the
right.
thing that you were worried if you, yeah, let me.
Like I would have gone through this whole calculation process and then forgotten to subtract it from 100 kPa. And then like I'm looking at the two values. I'm like, oh, well, 70 is closer to 93, so it must be that one.
Oh, that's why you want to set everything up algebraically first.
I get it.
See how I set it up like this?
Yeah.
So
So
I
then
know that,
you need to plug everything back in and you would have all the values accounted for.
yeah. So if you write things out algebraically first, you get to see the big picture. Whereas
Mhm.
if you just did the calculations, it's easy to get lost in that.
Do you remember one of the first problems in this, I think, let me just double check quickly. I really think it was the first one. No, it was not. It was a problem that was like, what is the value of like one ATM and it was equal to like 700 hertz or something?
Oh, so one ATM is equal to 760 torr, which is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals. And those are the ones that I can think of. But
It might have been HG, yeah.
yep.
760. Okay, so wait, but then if one ATM is 1,603 kilopascals, how did we get it to be 100 kilopascals?
Sorry, it's this.
Okay. All right. That's what I was really confused about. I was like, wait, if that's a value that I need to know, then what the hell did we just do here? Okay. All right. Makes sense.
Yeah, and then Pascal being equal to a Newton per square meter, I think is important too.
All right. So we're meeting tomorrow and then I'm taking it on Thursday.
Yeah.
What should I do for tomorrow? Because I have some time now today that I want to spend studying.
Make sure you get your. I mean,
Formulas?
yeah,
Yeah.
like if you
I
want
feel like I'm getting better, right? Like I'm
to.
okay.
Yeah, yeah. I mean, like if you want to use the paper cards, you can,
But
but
you
I would just say that you can do this. You can like mimic. Because I was thinking about this yesterday. Like, okay, you can still kind of mimic the benef beneficial effects of Anki if you with the paper cards, index cards, if you put them in different piles. Like,
hmm
let's say you make one pile for the easy ones, one pile for the medium ones, one pile for the hard ones, right? When you look at a card, and if it's easy, you can put it in the easy pile and review that easy pile with less frequency than the medium pile. Do you know what I mean?
Right.
Um,
Yeah.
so if you want to do that, you can do it that way. But the way that you wrote out the amino acids, like
It
just
doesn't
make sure that you're able to like draw it in like the straight line kind of structure that you would see it on the test. You know what I
hmm
mean?
Yeah.
Like if it's like CH2, CH2, CH3 or whatever, to be able to write that as like in the line form.
hmm
But I would say for yeah, tomorrow to
Oh, the amino acids in the formula.
for amino acids, the formulas, the functional groups,
Okay.
right? Like know what, to be like you should be able to get to the, understand them so much or know them so much that you are able to um
Teach them to you.
yeah, or like just
Okay.
draw an aldehyde, draw a ketone, draw a carboxylic acid, what do they look like? Um, draw, for the amino acids, the really important ones would be like the charged ones and the partial, aka polar ones, but to be able to draw them, and like, yeah. So like if you're reviewing them and stuff, like I don't know if this is what you're doing, but like when I'm imagining like how I would do it, I would be like, okay, if I see a card for valine, I would draw valine on like my notebook or whatever and see if it's right, and do it that way. So, so I think that if we just if you get all the like, equations down, functional groups down, amino acids down, uh, you're going to be in a good place. And yeah, you're learning a lot of like the physics stuff. You were able to explain it to me very well. So yeah, I think you're in a good place. So tomorrow, I would just say, just to yeah, get those three things down. Um,
Sounds good.
and then we can talk a little bit about test taking strategy. Like I can tell you about like a timing strategy that could work, and other stuff. So
Sounds good.
we can do that tomorrow. Yeah. So, but I would say to prioritize getting all the formulas down, functional groups down, amino acids down.
Beautiful. Okay, sounds good.
Awesome.
Um, I don't think my parents paid for yesterday. They were like they had a dance. They're still on this trip. So I whatever it is, they get back tomorrow to Boston. So
So yeah, I'll just,
sounds good.
text you.
Yep,
So,
sure.
all right, awesome. Keep up, the good work. You're doing good.
Thanks.
All right.
Bye.